Hello everyone. This is the next video in the series of videos looking at the second derivative test. So we've been using the sign of the second derivative to characterize critical points as either maximum or minimum points. We know that if x star y star is a critical point, if the second derivative is less than 0 at that point, then we have a maximum at the critical point. If the second derivative is greater than 0, we have a minimum at that critical point. Now, when we are discussing about the sign of the second derivative, we are easily able to label that if the second derivative is negative, it's a maximum. If it's positive, then it's a minimum. Then what happens when the second derivative is actually equal to 0? How do we characterize that critical point? Is it a maximum or a minimum, or is it a point of inflection? Well, the answer is that we'll have to fall back on the first derivative test to actually characterize these points. And we won't be able to use the second derivative test when f double prime is also 0. So let's look at a few examples to see how a few different cases where the second derivative is 0 and the first derivative test actually tells us, or actually helps us classify and categorize these critical points. So let's look at the first example. So I have the function y is equal to x to the power 4. So this is what, so this is what the function looks like. And yeah, so it's a proper U-shaped function. So to find the critical point of this function, I take the first derivative, and that's 4x cubed. And if I equate that to 0, I get the critical points of this function, and I find that x is 0, and there correspondingly y is also 0. So the origin is the critical point. Now let's look at the second derivative. So y double prime is actually 12x squared. And if I plug in the critical value of x into this y double prime, I find that the second derivative is also 0. So how do we characterize the particular critical point here in this case? From the image of the function, we can kind of say that the origin should be a point of minimum. So let's look at the first derivative test and try and see if we can characterize this point. So to the left of 0, what is the sign of my y prime? Well, y prime is 4x cubed, and 4 is positive, and x to the left of 0 is a negative number, so x cubed is going to be negative. Therefore, y prime is less than 0. To the right of the origin, y prime, which is 4x cubed, is actually going to be positive, because any x value that is positive, when you cube it, it's going to be positive again. So y prime is positive. So we know from the first derivative test that to the left of 0, the function is decreasing, and to the right of 0, the function is increasing. Therefore, the origin is a minimum. And we can verify that graphically as well. Let's look at another example where y is now minus x to the power 4. And this is actually just a mirrored image of the function along the x-axis. Let's go ahead and analyze it numerically. Y prime is minus 4x cubed, and when you equate this to 0, you get x is 0, and correspondingly y is 0, so the critical point is 0, 0. The second derivative is now minus 12x squared, and at the critical point, which is the origin, the second as well as the first derivatives are 0. So falling back on our first derivative test, let's understand what's happening to y prime to the left of 0. So y prime is what? Minus 4x cubed. So wait, let me write that down properly. Y prime is minus 4x cubed. So minus 4 is negative. X cubed, when x is to the left of 0, so your x is negative, so x cubed is also negative. Minus into minus is positive. Therefore, y prime is increasing to the left of 0. To the right of 0, we have y prime is again minus 4x cubed. Minus 4 is negative. X is now a positive number, and when you cube it, that is also positive. Minus into plus is minus, so y prime is less than 0 to the right of 0. So we have 0. The function is increasing to the left of 0 and decreasing to the right of 0. Therefore, the origin is a maximum point. And we can also verify that from the graph. Right there. Now, we move to the third case, which is y is equal to x cubed. You find the critical points in the usual way. Y prime is 3x squared, put it equated to 0, you get the origin to be the critical point. And you can compute the second derivative, y double prime. And at 0, 0, the second derivative is also 0. Now notice from the graph that when you have a function y is equal to x cubed, the origin is actually a point of inflection. So what will the first derivative test show you here? So if you do the first derivative test, to the left of 0, y prime is going to be 3 times a negative number squared, which will be positive. Y squared is going to be greater than 0. Sorry, y prime is going to be greater than 0. And to the right of 0 as well, y prime is going to be greater than 0. And because the sign of y prime does not change, we know that the origin is an inflection point. Now, I want you to do something extra here. I want you to look at the sign of y double prime as we go from the area to the left of 0 to right of 0. Now, I'm not asking you to look at the sign of y prime, but I'm asking you to look at the sign of y double prime. So sign of y double prime as x goes from 0 minus to 0 plus. Let's use this color. When you're to the left of 0, y double prime as 6x is actually less than 0. When you're to the right of 0, y double prime, which is 6x, is now actually positive. Now you see how y double prime is actually changing its direction from less than 0 to greater than 0. And can we see that in the graph? To the left of 0, this part of the curve, my y double prime is less than 0 here. It is concave. And in this part of the curve, my y double prime is greater than 0, so it is convex. So the idea is that when x0, y0 is a point of inflection, the second derivative is also 0 at that point, but the second derivative changes its sign as x passes through the point of inflection. And that is precisely what is happening here in this example. So that brings this video to a close. So thank you for watching. I will now stop sharing and I will stop the recording.